Welcome back. We're going to continue looking at metabolism here and move on to the next stage, concept 9.4. So during oxidative phosphorylation, chemiosmosis couples electron transport to ATP synthesis. So here's our overall schematic again. We've created all these electrons. Now, what do we do with them? Well, we put them into this system called oxidative phosphorylation, which transports those electrons, pumps protons across a membrane, producing an electrochemical gradient, and then we're going to utilize that to drive the generation of ATP. So let's stop and focus in on this last step here. So recognize that from glycolysis and the citric acid cycle, we're generating these reduced compounds, which have electrons that they can now donate onto the electron transport chain. Each one of these carry 2 electrons, and ultimately we are going to use this to power ATP production. So, if you guys remember this paradigm, we have an electron donor, which gives us a high energy electron. We put it through an electron transport system, which pumps protons. We ultimately will take those now low energy electrons, because we've used up their energy in here, and put it on the oxygen making water. All right. So also keep in mind that, as opposed to burning something, releasing a lot of energy explosively, we are essentially taking those electrons and passing them from one thing to another, to another, to another, to another, in order to glean that energy. This is an overview of that system, modeled in 2 ways. So here we have a scale along the y-axis that is the amount of free energy present. So here we have electrons going on to oxygen, which are very low energy. The electrons coming in from NAD are very high energy. What's going to happen is they're going to be passed through these large multi-protein complexes. Within these protein complexes, we have various groups that can become oxidized or reduced. Again, you do not need to know any of these. Okay, this is important just to give you perspective, right? So here we take those higher energy electrons, we pass it on to this, so this compound becomes reduced. Then it passes those electrons on to here, those become reduced, then this, then this, then this, then this, then this, then this, then this. Ultimately, those electrons are now low energy, and we get rid of them. There's another pathway coming in the side here, and they can join at this point here, this Q entity. So this is not what it actually looks like. This is more what this system actually resembles. So here we have a biological membrane. Here we have the matrix of the mitochondria. So the very inside, this darker orange is the inner membrane space of the mitochondria. Here we have complex 1. We dump those electrons onto here. That passage of electrons along all these little centers and ultimately on the Q changes the protein conformation. As the protein is changing shape, it pumps proton. Okay, here we have another molecule who is taking those electrons from FAD, and they're passing it off onto Q. There's actually several things which can join dumping electrons onto Q. Q is hydrophobic and will stay in the membrane. It's simply an electron transport vehicle. It will then dump it onto this complex, This will again pass through several centers and onto something called cytochrome C. That is going to pump more protons. Again, we move electrons. That's going to cause a protein fold change. We move it again, another change, and that process pumps a proton. Once on the cytochrome C, we transport it onto the final complex, and here we continue to move it through centers, ultimately dumping it off onto oxygen. This again is transporting protons across this membrane. All this energy is stored in a hydrogen ion gradient, right? So we have a high concentration of ions that we are generating on one side of a membrane. We can then utilize that to drive ATP synthesis. This gradient is called the proton motive force and has the capacity of doing work. It is essentially a biological battery. So here we take all those protons, and one place that we can send them to is this thing called ATP synthase. This is essentially an ATP generator, and I mean that literally. You have a turning apparatus that has stuff flowing through it, and that is what is generating ATP. Okay. Now, something for you to consider is this intermembrane space also exists in bacteria. Bacteria also carry out this process just like your mitochondria do. In bacteria, it can also use this proton motive force to operate other things. Okay? Those other things include a little propeller-like thing, which unfortunately is also called a flagellum, but it looks nothing like the flagellas we've discussed before. It is more akin to a little propeller. You can use this proton motive force to import nutrients. Okay, and in the mitochondria, this is actually what is bringing in various things that the mitochondria needs. So let's zoom in and take a look at this ATP synthase. I said it was very akin to an ATP generator. Let's give it more detail. Okay. Here in the membrane, we have this fixed structure called the stator, and that is coupled to this thing called the catalytic knob. This does not move. This does not move. This has a pore going in and a pore coming out. They are not connected. This part right here is called the rotator, and it is attached to this internal rod. This does in fact spin around as protons, which are high concentration outside, flow in. They hit these binding sites. The proton that is in the site over here will leave. That is going to then cause a rotation to occur. A new proton comes in, a new proton goes out, turn, proton in, proton out, turn, proton in, proton out, turn. And you can see this is essentially the same function as a water wheel. So here we have water flowing in from the top. It comes into these little buckets on this wheel. It turns the wheel, and this wheel can then turn a generator generating electricity, or it can be turning a millstone to grind wheat. Okay. Now, this is ultimately turning this internal rod, and that internal rod is going to cause a conformation shift in this catalytic knob, which again is fixed. So here we have this fixed catalytic knob, and it exists in one of three conformations. So it's made up of two alpha beta, so here's an alpha beta subunit, another alpha beta subunit, and another alpha beta subunit. The beta subunit is where the action takes place. Here is this central rod sticking into it, and notice that it is asymmetrical, has three different surfaces. those three different surfaces are going to cause that beta subunit in contact to form one of three conformations, either open, loose, or tight. So you have ADP and a phosphate come in and bind. You get a rotation of gamma. That is going to cause it to switch to a loose conformation, whereas holding these two things. It will then rotate again, and that will turn it into the tight conformation, which is what causes the ADP to fuse with that phosphate, creating ATP. It'll rotate again back to the open conformation where that ATP can fall out. Let's take a look at how this looks. So here you can see the central rod rotating. It is asymmetrical and is causing each one of these proteins to form one of three conformations. And that is how we make ATP. Let's take a look at that from the side. And you can see that this is causing a major mechanical movement. It is this mechanical movement which is causing the generation of ATP. So again, we have this whole system set up here. We have glycolysis, giving electrons, but also doing some ATP. We then turn it into pyruvate and put this into the citric acid cycle. This produces a lot of NAD and also FAD. All of these electron carriers get dumped into this electron transport chain, which produces an electrochemical gradient, pumping protons, that runs through ATP synthase, which is a proton ATP generator water wheel type thing. That produces about 26 to 28 ATPs per glucose. This gives a maximum amount of glucose of 30 to 32 ATP per glucose molecule. So we get a couple here, and then 26 to 28 here. Why is this not a uniform number? Well, remember that proton motive force, all those protons living in this intermembrane space, can also do other work, such as facilitate the driving of import of various molecules that are necessary for the citric acid cycle to continue, or to move molecules out, bring in other things. So we don't get 100% efficiency here. So we actually have a range that we can operate under. So the biggest thing, biggest takeaway, memorize this. This is what you need to know, okay? Understand the flow. In addition to that, if you can kind of take into account that all of this is producing electrons which dump into this, and this is what happens. So we have this electron transport chain in a membrane. We pass the electrons. They get harvested energy. We keep on swapping. We ultimately dump them onto oxygen and producing water. All this energy that we gleaned causes a mechanical shift, which pumps protons. That produces a proton motive force, or a high proton gradient, which then drives the production of ATP, okay, through this water wheel generator. As a side note, imagine what would happen if you use this ATP synthase and instead of consuming or producing ATP, we consumed it and ran it backwards. It would, in fact, pump protons the other direction. And so in our stomachs, where we produce acid, we essentially have something very analogous to this ATP synthase sitting and working in reverse. Then burning ATP to pump protons into a space. So a very multifunctional system.